Hi everyone, thank you for joining the live Q&A with Holgar. I hope you enjoyed the lecture earlier today where Holgar talked about the evolution and the future of IBM quantum hardware. And I was very excited to watch the lecture because it's dear to my heart. I have an experimental background, and so I really I know how much like work need to go into done to make all this thing happen. And if you don't know me yet, I'm Jin Ye. I'm the global lead for coding challenges, one of the organizers for the summer school, and really excited for all of you to join us. And just a brief introduction about Holger, which you can also find on Discord on a longer bio. So Holger is a staff research scientist in IBM, and his work really focusing on maximizing the hardware performance to enable utility scale quantum circuit executions. Um, so just like we have this issue a few times, he just disappeared. So I hope you will join soon. Yeah. So let me see. We can wait a few minutes, but I can start answering a few questions. And you can also use the Q&A panel here to add questions. And you can also upvote each other. Hopefully by now you should know how this works. And I think Holger is back. All right.
Uh, I think I'm.
Yes. Can you hear us?
Uh, yes.
Okay. As we predicted, this is going to happen. Okay. All right. So I think we can get started with some questions that we pick up from the lecture. So one of the main, a few people asked this question is about alternative qubits that whether IBM is pursuing, and what do we see about that? And maybe you can elaborate on that.
Yes. First, before I get into that answer, I want to thank the organizers for organizing such a great summer school. Once again, a lot of work has gone into it, and I really want to appreciate that. And of course, I want to thank them for having me here. It's a true pleasure. As for alternative qubits, this is something that always comes up as a question, whether in the form of people ask it, other types of qubits, or even in the realm of superconducting qubits, um, and the way I see it is people tend to be hyper focused around what type of qubits you use and not see the problem of quantum computers as a sort of system engineering problem, as I kind of try to lay out in the lecture, that it's a lot more than just picking some perfect qubit with a perfect coherence, or even more so with some like particular aspect that happens to be hyper optimized for that qubit, so you can go and really emphasize that, oh, like this aspect of the qubit is great. I think the reality of building a quantum computer is a lot more messy. It means making a lot more compromises, and the architecture actually the, is much more in between the qubits than within the qubits themselves. I mean, you can even think about classical computers. How often do you hear a reinvention of a transistor? You measure these time scales in decades. Um, so really, when you think about it, you 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 need to look for a platform that has all the elements that you need in terms of reset, readout, gate fidelities. You need to see that you also can scale it out and really scale it out to the scales that you need for fault tolerance eventually. And it's almost guaranteed that on every aspect you will be making some compromises. So, I mean, I would say, like making qubits is really the easy part, and you shouldn't. If this is where you're stuck at, then you're really at the beginning of the road. Um,
Yeah, I think that that's great. Yeah, it's like making one qubit is it's just the first step, and it's a
right.
whole system engineering hardware, like one qubit, a few qubits, and then the chip, control electronic, cryogenic infrastructure, all the software and control and everything is so complicated. And actually, we'll hear a few things about this kind of topic throughout summer school. Like later today, we have Professor DiVincenzo to talk about the DiVincenzo criteria. When in the early days that people still don't know which kind of hardware platform to choose, and he create a framework for us to choose and there's criteria. So among like I don't know dozens of different things, now we are down to like a handful: spin qubit, chat ion, neutral atom, and all those things. So hopefully you can tune in later to watch. And then tomorrow we will also have a distinguished lecture about our very own Jerry Chow. He will share the story of how we put a quantum computer in the cloud, which maybe you think is like, okay, you just connect a cable to your quantum computer and that is done. But you will realize, hopefully, you will share more like the whole software stack and everything to make sure the system is reliable, connecting to the cloud and getting jobs from like hundreds of thousands of people. So really, there's a lot of things going on to make a computer work. Like first qubit is the very first step. Yeah. So we can move on. I think we can take some questions that are already in the chat here, which has a lot of upvotes. So there's one question, the top voted question is, why is it difficult for superconducting qubits to create entangled state between qubits that are very far apart?
Yeah, this is a great question. So you can think of it like this: that if your architecture has only um, nearest neighbor couplers, for example, like our Heron and Nighthawk processors have, then to create an entangled state um, between qubits that are far apart, you need to do many, many 2-qubit gates between them. And each of them comes with some error. So the success probabilities will just multiply, or the fidelity will basically be a power of an individual 2-qubit gate fidelity. So that's why for that kind of architecture, this is difficult. Now, of course, as I showed in the lecture, you don't need to build superconducting quantum computers only with nearest neighbor couplers. There are ways of building them with uh, what we call C couplers that connect distant qubits, not nearest neighbor qubits, or on the chip. But this comes with its own set of challenges. I mean, for the pretty much for the entire history of superconducting qubit, you have heard that their couplings have to be nearest neighbors. So I think this is an aberration. I think this will change. There's really no sort of fundamental reason why it should be that, but um, the difficulties there are now the coupling elements that you build that connect these distant qubits have to be shielded. Now with any element that's a microwave element that has significant length, and that extends to, sort of centimeter scales, you will start having modes that you maybe not necessarily don't want to deal with. So this becomes an issue, and also there are, of course, just plain sort of manufacturing issues with with producing something like that. So so that side of producing these uh, distant entangled pairs is somewhat distinct from having to do these nearest neighbor two cubic gates. Um,
Mhm. Yeah, I think like it's to me, I think it's I because I have experimental background, I can imagine how difficult it is to do like very distant, and I see like L cover like even like 1 meter long is it sounds like crazy, and you still get I think like 90% fidelity. That's really awesome. So I think we can move on
right.
to the next question, which is very interesting. So basically, is how do you make a quantum computer by yourself, a DIY computer, if someone want to do it?
Um, yeah, that's a great question. It was uh, somewhat addressed in the lecture and maybe with the first question too. Um, you you really have to think through um, how what will be the hardware that will basically address these Stevens-Inzel criteria. So uh, what will be what will be your qubits? How can you implement two qubit gates, single and two qubit gates between them? How can you reset and read out these qubits and do that effectively? So and also your qubit states have to be long lived, so your coherence times have to be sufficiently long for all of this to work. So, um, and then after that, then you need to start thinking about all the control electronics that goes into it that we saw in the lecture, these racks and full of control electronics that basically are assigned to each qubit to perform these gates and to also do the readout, and then next step on top of that is now you need electronics to implement error correction. So you need, uh, depending now on the speed of your uh, qubits. So by speed, I mean really the gate speeds and measurement speeds. Um, you will need something that will process the um, information that comes back from the measurement that will now implement error correction on your architecture. So it's it's quite a handful of tasks to take on if you wanted to go about doing that. Now, if you if you want to build um, a small quantum computer, let's say up to like um, uh, 2 qubits or so, then and if you're willing to cut some corners here, do some instead of single shot measurement, you're willing to do ensemble measurements, then you can imagine doing some like, for example, NMR based little setups that you can really wire up in your garage too, and you can build a simple uh, 2 spin NMR setup pretty easily and perform some basic measurements on it and put an AWG card into your computer and it will work. It's and you know you can do a C naught with it.
Yeah, sounds like it's a bit like you try to do this and then you will be like kind of looking at the historical development of what people do first, and that was NMR because that was the easiest. And then if you have a bit more budget or you have a bit more equipment, maybe you do a chap ions or something. I imagine. Probably superconducting qubit would be the hardest because you need to buy a fridge first. That will cost you a lot of
Right,
money.
right,
Maybe some room temperature things would be easier. Yeah.
exactly.
Yeah. Okay, that was a very fun one. So we carry on with other questions. So the next one is people asking that most resources that you can find online about quantum computation usually is about like maybe algorithm or programming, like what we do also, rarely about more engineering or like the hardware. Do you have any resources that recommend, a book or some maybe archive article or maybe some thesis?
Um, the, there are great resources if we narrowed it down to superconducting qubits, then there's an article, I think it's called Engineer's Guide to Superconducting Qubits. If you really want to get into
Hmm.
sort of
This is
details
from
of how to,
William Oliver.
yes, exactly.
Okay.
Um, um, into the details of various aspects of it. Now, um, for other platforms, I'm not that much of an expert, but I would say it's always interesting for me, as I'm here telling you that building quantum computers is more than like these small demos, and you need to think about how to scale them up. I like to look at um, uh, companies, various organizations that are undertaking these efforts, and actually just their white prints, YouTube videos that they put out on it are often quite helpful resources to like get going, get some some understanding of um, what are the ingredients that go um, into their setups. Like in the case of IBM, it would be the roadmap. You would start with something like that, or summit videos, and then you would follow by just sort of narrowing it down to specific aspects that you pick up from that.
Mhm. Yeah. So I personally also have a hardware background, not exactly qubits, but I think the engineering guide to student give it probably the best place to come in, like a summary and it's very specific. But I think maybe once you get into maybe doing a PhD, what find helpful is reading people's PhD thesis. There you see a lot of details of like things working and not working, things that people try, and some detailed thing that maybe not worth mentioning in a paper. But then when you actually go to do it in your lab, if you are in a lab that have no prior expertise, that's where you find the most. For in my case, it was like that. I was trying to do some experiment that my lab just didn't have anyone knowing those level like sensitive. I have to read papers and emailing people. So if you get to that stage, maybe those that would be useful. But I think to get started, probably some review article and some video to
Exactly.
get some more detail. Yeah. Okay. So we can move on. So this one was in the lecture and I answered. But I think would be good to. I think it's a very interesting one. Is like what kind of it's a bit like reverse of the previous question. It's like if you care about only algorithm, then what are the hardware you need to know so that you can maybe get the most out of the how like the doing this algorithm.
Yeah, no, that's a great question and like very uh, pertinent at this day and age. Um, since we don't have fault tolerant quantum computing, then any implementation of your algorithm, you can probably eke out a little bit more performance by knowing the underlying noise properties that are particular to your processor or the particular to architecture. So why is that so? Because if you know that, then you can start picking uh, various tools to tackle that, like dynamic decoupling, for example, is something that is very widely used. Various twirling techniques, of course, for both gates, readouts, and so if you have, um, I I don't think you need a a super deep understanding of the sort of, for in the case of superconducting qubits, like chip level um, uh, performance, uh, or chip level sort of architecture, but you need to know the what's the outcome of the design in terms of noise, and what are the particular residual couplings between the qubits and so on. What are the crosstalk properties? So that definitely helps you to squeeze out a tiny bit more performance, and it always helps to know various experiments that you can use to characterize uh, these relevant properties. So,
Hmm.
for example, how do you measure the what kind of noise you're dealing with? What kind of what's the level of crosstalk in your setup, so that you can quickly characterize it and then tailor your uh, algorithm, your circuits accordingly. Um,
Mhm. Yeah, that's a very good point. So in fact, in the next 2 days of the summer school, tomorrow, Friday, and also Monday, we'll cover a lot about this. Tomorrow we'll talk about the algorithm and the techniques like transpilation, error mitigation, and those things. And then next Monday we'll have an extra talk just on benchmarking, which is what you're talking about. You can run some stuff to characterize your this circuit, your chip. Then you can then decide on what kind of error mitigation, or maybe to choose certain qubits, or maybe do some other thing to treat that they have some noise in this, and you may use more dynamical decoupling to reduce or crosstalk and all these things. So I think that will be interesting, and hopefully participants can learn more from those talks. All right, we can move on to the next one. This is kind of similar to the first question. Do you want to take still is about alternative qubit, but on optics? I don't know what much we can say about that.
Uh, yeah, I mean, I would sort of say that, like, in some sense, we've already addressed it. That it's it th again, I would say we have the roadmap. We have it for the next 10 years. If you look at our roadmap, and if you look at just in that PDF, some of the sort of designs of what that will mean in these coming years. These setups are going to be needed data centers effectively. So um, so you really need to make a plan. You need to commit to it, and you need to be uh, hyper focused on executing, because otherwise, these these are extremely large scale projects, and there's no hope of delivering them without that. Um, in terms of optics, I would just say, in some sense, photons are kind of perfect qubits, of course. So, the polarization of them, you can look in the sky, and you see in the cosmic microwave background from whenever the universe cooled down, it's still there. but they have a few issues. One is they tend to run away from you at the speed of light, which is formidable, and they they also that's the thing. People are hyper focused about some particular aspect of these qubits. Their coherence, in some sense, is extremely long. At least if you look at the polarization, but it's because they don't really interact much with anything, or it's hard to get two photons to interact. Um, so it's a double edged sword, um, and um, and having or making detectors for photons is a huge issue for these architectures. Having them have their uh, fidelity or that is needed for delivering these particular codes that are envisioned for them. So um, there there are always trade-offs as with any other platform, and uh, there's you win somewhere, but you certainly lose on other fronts where with optics.
Mhm. Yeah. Yeah, again, I think later the lecture on the on Vincent will maybe help, at least in the early stage, that how people try different approaches and then the criteria can help to frame that. But but also there's a lot of different challenges once you scale up to. I think when he was thinking about this probably was small scale, but now if you think about 1,000 or million is also another challenge. Okay, so we have 3 minutes left. I think we can answer one more. Next one is about FPGA. How are they
Uh,
yeah, contributing the control electronics?
um, yes, that's also a great question. The short answer is FPGAs are left, right, and center everywhere because they really provide you a way of fast digital generation of signals and also processing of signals. So, because like we've been saying here in the lecture, you need gates for manipulating your qubits, and for um, uh, error correction. You need to make these error correction decisions with extremely low latency based on the measurement outcomes. Then you need something that's almost purpose tailored for your particular um, application. So FPGA short of ASICs is like the closest thing that you can get for these applications. The next thing is of course purpose tailored ASIC um, uh, chips. Um, and now it depends. I alluded to it earlier too. It depends on the type of architecture you have. If your gates and measurements are slow, then you can afford to do things on CPUs, GPUs too. They don't necessarily have to use FPGAs, but uh, now what you run into is it can slow you down in your error correction cycles to rates where even though you in principle have an error corrected quantum computer, it might effectively be still useless because your cycles are so slow. Um, so it the throughput question is very important to for when you're considering architecture.
Mhm. Yeah, I think that is really, really cool. Like it really depending on the system you're using. And I think again to point to the next talk we have from DaVinci, I think that will really help to like lay out a framework to decide on different hardware. So with that, I think we finished all the question for Q&A. But just to wrap up, I think it would be interesting to hear from you, Holger, that if someone is really inspired to become like someone doing what you do in hardware research, we all touch upon some of these like resources and things, but it would be good like to hear from you. Do you have any tips for people like starting in summer school and want to pursue like a experimental uh, career in quantum?
Yes, I mean it's a first tip number one. It's a bit larger, or it's not even quantum computing or hardware specific. I would say what has helped me enormously in my life is find good mentors for yourself. Um, this this really has been, I would say, what I would credit almost all of my career to, and not just in academia, but outside of academia, or if you're in academia, then not just your supervisor, uh, but um, mentors outside of that, and people who can connect you to industry in a more meaningful sort of mentorship way, rather than just be a sort of contact on LinkedIn. Um, in addition to that, there are certainly skills that will help you along the way. Uh, in particular, I would say um, knowing about electrical circuits, knowing basic instrumentation to perform measurements is kind of essential. You don't have to be maybe a complete expert, but having some being acquainted with apparatus and some simple circuit modeling is always helpful, just to understand what's going on around you. Coding also is, I would say, an essential skill almost everywhere. Um, you could argue that in some hardware fields, maybe it's used less so. I'm thinking in particular, maybe like fabrication heavy um, career paths, but I think it, I would contest that. I think it's helpful everywhere, even to be able to analyze, organize your experiments. It doesn't have to be at a software developer level, but just um, sort of basic skills. Um, then I think this kind of covers it. We've already run over time. I don't want to
Yeah,
take up too much
that's
time.
great. Given I can associate how I ended up in IBM Quantum also due to a mentor that is in IBM when I met him in a Kiski Camp, IBM organized event, and also programming was useful. And then now I'm not doing experimental research, and so the extension all the transferable skill I have are mostly what I learned programming. Now I still use programming, so that is definitely a good skill to have no matter what you do. Uh, all right, so then I think we are wrapping up here. Just as I already reminded many times, so you can tune in 1 hour and a half now that you can see a distinguished lecture by Professor David DeVincenzo, where he will tell you about the historical perspective of how the early development of different hardware and how we came out with the criteria and how we can decide on like which hardware is more promising for different reasons. And also later in this day, we will also have a walkthrough for lab two, which we focus on like the techniques, like error mitigation, which will be actually covered tomorrow. But we know that many part of the world tomorrow will be too late, by Friday. So we'll give you the lab already today, and then tomorrow you can already tackle them. But the main concept that you will learn will be covered later in tomorrow's lectures. So yeah, and then see you later, and thank you very much, Holger, and thank you everyone for joining.